everyone, hope you've had a good half term and hope you're all doing well. So it's a quick video to help you with part of your waves work for this week. So most of the wave stuff's pretty simple, so you should quite easily be able to go through the stuff where you're just labeling up the wavelength and the amplitude and the frequency. It's just about also learning those definitions. I would say though, especially frequency, that definition is really, really important. So the number of waves that go past a certain point in a second being frequency, really important sort of key term. We've talked about frequency a little bit before in other like kind of topics, but it's always the same thing. It's always how many of something in a second. Right, so the bit of this is most complicated, I feel, is the transverse and longitudinal waves. Some of you might even remember this from year 8. It is something that you will have done before. And looking at two different types of wave and comparing them, and it's really easy to get confused with this. So the reason for that, well, I'll go through the reason for that in a minute, but looking at this for a start, this is a transverse wave, and we can see it's a wave because we can see if energy is being put into this side by, imagine this is just a rope, and you're moving one side of the rope up and down. That energy is being transferred through the wave from here this way. So that shows us the energy. And that makes it a wave. A wave is just a way of transferring energy. It's just transferring energy from one place to another, but without the particles actually going anywhere. Because if you focus on one of the red particles now, and this is kind of a bit counterintuitive. If you think about water and waves on water that look a little bit like this, it looks like the water's moving this way. But then think if you popped something floating on the water, it wouldn't move with the waves, it would just bob up and down. If you had like in a bath or in a sink and make a wave like this, and you've got something floating on top, it would just bob up and down, as long as the waves aren't too violent and throwing it everywhere. But the energy's moving, but the particles are not, and that makes it a wave. So what are the particles doing then? So look at the particles. That's quite a simple one. The particles are moving up and down, okay, moving up and down around a fixed position, and we call that oscillating. So the particles are oscillating, and that's the way they're oscillating. So we call that the oscillation of the particles. Now in this case, and this is where people get confused, and this is where people lose marks on this, so don't write this. People would quite often say the particles oscillate up and down, because you see it like this, because this is the easiest way to show it on a piece of paper. What if you turn the wave that way? Okay, now the particles aren't oscillating up and down, they're oscillating side to side. It's not about the direction they're oscillating in. If you put it at a funny angle like that, then what do you say? So the particles don't necessarily oscillate up and down, but they do always oscillate at the same direction compared to the energy transfer. And if we look at what angle we have created there, okay, so look here, we've created a right angle. So the energy transfer is perpendicular at a right angle to the oscillation of the particles. And that's what you'd always say about a transverse wave. Okay, so just to write that out, to make it really clear, energy transfer is perpendicular to the oscillation So energy transfer is perpendicular to the oscillation of particles in a transverse wave. That little sentence there, that's what you really need to remember. Okay, you need to be able to label these waves as well, but this thing here is the main like bread and butter of this. That's if you get asked something in an exam question, that's your answer. Okay, so examples of this, I've already mentioned water waves are like this. Light waves, radio waves, anything that's an electromagnetic wave, which we'll come on to in a few weeks' time, anything like that looks like this. Okay, moving on then to longitudinal waves. So I've put two versions of this because it's kind of a bit harder to see what these are. But basically, what a longitudinal wave is a series of compressions and rarefactions. So I think these words are quite obvious what they are. Yeah, spelled that right, yeah. So it's quite obvious what these are, because a compression, it's compressed, it's squashed up. A rarefaction is where the particles are rare, so they are far apart. And if you look at the moving image at the top, you can see how that's happening. So on a slinky, you could do this, and if we were in class, we would be doing this. You can squash the particles up and then pull your hand back, and that will transfer energy through the wave. So again, we've got a transfer of energy through the wave going that way. Okay, so going through there, we've got the energy transfer. And again, we know it's a wave because energy is being transferred, but again, watch one particle. So pick one thing on the wave, it's going this way, and then it goes back again. So you pick one, it goes that way, and then that way. Each individual spring is just going backwards and forwards. So that tells us that the particles are not moving, they're oscillating. They're not going anywhere, they're moving about a fixed position, they're oscillating. But this time the particles are oscillating this way. Okay, so that way there is, it's a bit smaller, the oscillation of the particles. Now, we said for a transverse wave that the energy transfer is perpendicular to the oscillation of particles. In a longitudinal wave, and you can probably see this, they're not perpendicular. They are going the same way, basically. And two lines going the same way, we call that parallel. So we'd say energy transfer is parallel to the oscillation of the particles. In a longitudinal wave. Okay, so in a longitudinal wave, energy transfer is parallel to the oscillation of the particles. And again, that is your key bit of information that you need to take out of this. So I'll just label a few bits on here as well. Rarefaction and compression. So basically, that's the comparison. If you're asked to compare these two waves, that's the comparison. In a transverse wave, energy transfer is perpendicular to the oscillation of particles. However, in a longitudinal wave, energy transfer is parallel to the oscillation of particles. Examples of this, you could have mechanical waves for both of these actually, because you could produce the same wave mechanically, means just by physically moving it. Or the main one that's just a longitudinal wave is a sound wave, because sound waves are just basically, if you think about what a speaker does, think about the way a speaker moves. You can see like a big speaker with like a big bass speaker, and it's moving forwards and backwards, and it's pushing the air and then pulling it back and pushing the air and pulling it back, and it's creating areas of compressed particles and particles that are not compressed, that are spread apart, they're rarefactions, and they travel through the air as a sound wave, get to your ears and make your ears hear things. So that should be it. That's basically the most complicated part of this, is this bit. Okay. Only other thing I will go through is considering, I think it's quite difficult on the last question on the worksheet, the wavelength and the frequency. So think about this wave here. If I squash this up, can I do this? Yeah, if I squash this up, okay, so I reduce the wavelength. If the wave is going at the same speed, the frequency will increase, okay? So if the wave travels at the same speed, and that's the thing that's got to happen, it's got to be the same speed, the smaller the wavelength, the higher the frequency, because you're going to get more waves going past in a second because there's less distance between the waves. It's quite simple, like speed, distance, and time. If they're traveling at the same speed, but there's more waves in a second, you're going to be having a shorter wavelength. So higher the frequency, the shorter the wavelength, bigger the frequency, the lower the wavelength, but it's got to have the same speed for that to be true. Okay, that should be it. I think the rest of the worksheet and the rest of the little questions and everything I've set for you should be relatively simple this week. So I'll leave you to get on with that now.